Okay, let's get started. Welcome to the fourth talk of the Martin Center Research Seminar Series of the Easter Term 2021. This seminar is hosted and supported by the Martin Center for Architectural and Urban Studies at the University of Cambridge. And the theme for the annual series this year is architecture and energy. I'm Louise, one of the conveners of this year's seminar series. Today, it is our great honor to have our speaker, Dr. Neveen Hamza from the University of Newcastle, and our chair, Professor Peter de Wilde from Tourism. Welcome both of you, and thank you for joining us today. And before the talk, let me go over a few housekeeping stuff for the seminar. And today's seminar is going to be recorded, and we will upload the recording to our YouTube channel after the talk. The talk will be around like 40 minutes. It is live streaming on Facebook until we open the channel for questions. There are several options to join the Q&A section. You can click the raise hand button under your screen, and in this case, we'll invite you to the Zoom panelist, and you can turn on your camera and your microphone and join our discussion, and you can discuss with our speakers on our chair face-to-face. And alternatively, you can also type your questions in the Q&A box and send to us. And also, if you have any comments, you are also very welcome to send it to us using the chat box. And now I would like to hand over the mic to our chair today, Professor Peter de Wilde. Thank you.
Thank you. Good afternoon, or good morning, or good evening, wherever you are across the world. I'm very pleased to chair the session today. I'm going to introduce today's speaker, which is my good friend, Dr. Neveen Hamza. She's a reader at the University of Newcastle in the area of architecture, energy, and well-being. I know her from a lot of work in the building physics, building science domain, where some of the first work I was involved with her was actually on airflow, and I think that's very important in today's talk. Neveen has a background. She did her PhD and MSc in Alexandria University in Egypt, and then had a PhD from the place where she works right now, which is Newcastle University. She's had a number of honorary positions, amongst others on the board of ABIPSA England, where we serve together. She's a board member of the Tyne and Weir Building Preservation Trust, and involved with European research as well, where she sits on the Associate Peer College for the funding for science and technology, and she's been on the board of the Arab Society of Computer-Aided Architectural Design. She's also done a number of research projects, some with me, some in other areas. So she's worked with the Wellcome Trust, Horizon 2020, Europe funding, AHRC, EPSRC, and British Council projects. So that's a lot of things that feed in today's presentation. And more recently, she managed to win a prize with her students, I think, for the Cool Abu Dhabi series on urban comfort and sustainability. She has a distinguished track record with 6 book chapters, over 25 peer-reviewed academic journal articles, and more than 65 conference papers. So I think that feeds all in today's presentation. Neveen, I look forward to hear you. Over to you.
Thank you, Peter. And thank you, Cambridge team, for inviting me today. And as usual, I lose my voice. Okay, thank you for the audience as well. I think my presentation today touches very much on the situation we're in. We can't share air, and that's a real tragedy. But for now, let's look at how air has influenced the shaping of architecture and our experiences in those buildings. And most of all, why we as architects really need to see it as a material. Okay, and I think I need to share my screen, which I haven't. Oops. Okay. Can you see the presentation?
Yes, the can see it.
Yes.
There you go.
Right. Okay. So now, instead of giving you a lot of scientific definitions, let me just introduce you to how air taught, what air taught us about human relationships. A wealth of things, really. It doesn't like high pressure. It likes to move from high to low pressure. And if you choke it or constrain it, it will increase its speed and it will escape. When it hits an obstacle, it separates and it creates a stagnation point where the velocity is 0. Very similar to our human relationships, creating turbulence in its wake. When it's cold, it's dense, and then it doesn't like overcrowding, so it would move to a warmer environment and where the air is less dense. It's a medium, so it also carries a lot of our olfactory experiences, whether good or bad, and it allows radiation through it, so it can be warm or too hot. It's also buoyant. It likes to move upwards from cold to hot, and it's invisible, yet has a very, very strong and potent effect on our feelings and how we behave. We can keep it healthy or intoxicating, and undertakers know this secret very well, captured by this very intriguing topic about undertakers knew the truth about the great smog, but they also know the truth about air carrying viruses, being high in its air pollution content. That means more business for them. We all know that air pollution and how the air behaves has a lot of secondary influences on our health. Ranging from effects on our skin to our hearts to our brains. And if we can't appreciate it, we lose it. And it's a tragedy when we can't share it, which is the situation we're in now. But at this point, I would like to look at very, very quickly, and this is quite a challenge to try and go through the history of the architectural legacy and how air actually had an influence on forming it. So while air is the most invisible yet more valuable material, we actually as architects leave it to perform by chance. Air played a crucial role in forming plan sections, elevations of buildings, till the discovery of air conditioning, where we decided to machine air. Architects provided the aesthetics of ventilation in an accidental attempt to provide air indoors. Building services engineers, on the other hand, had to comply with minimum levels of air change to reduce energy demand on buildings, and totally machine air was always an easier calculation. So the mantra was seal the building, occupants are lazy, and just let the building system do whatever it does. But air has actually had a major role to play, and if anything, if we review the architectural legacy, it actually tells us something about who's breathing this air. So if you look at ancient Egyptian temples, you find that the great court here that was meant for the public, the common people, to come and appreciate the king and the elite priests, they were really allowed through a very small door that would humble their existence into this courtyard that was not shaded at all, to be left in the sun, feeling very uncomfortable with the temperature of air, while all the priests and the elites of the government would enjoy the hypostyle, where for the first time the idea of clear story is introduced and the hot air would rise up, leaving them feeling cool. Courtyard houses, as often mentioned in literature, are another case of understanding how air differentiates between people, because the wealthier the merchants were, the wealthier the owners were, they would have ownership of bigger courtyards and architectural systems. And it's important to mention the word systems here because they were not elements. Vernacular architecture worked on the principle of systems. So the air pressure differences between the openings, the wind catcher, and the courtyard would all interface together to provide a comfortable environment. If you look at this idea of the expression of air and wealth, it also finds its way in Chinese architecture, and it's important to mention Fuzhou. That started in the Tang dynasty, 581 CE, and these houses are still being used till today after a major rehabilitation project by the government. But if anything, they show us how, again, the elite constructed their buildings with sustainable materials, very expensive wood, and provided those courtyards lavish in their landscape with their pools just to temper the air in what we would consider vernacular architecture. And if we go further to Cairo again, where we look at the 16th century houses, courtyard houses, Beit al-Sahimi, for instance, lavish with its courtyards and very large areas of openings, almost 90% window-to-wall ratio that are covered by beautiful constructed wooden lattices that capture the idea of how air moves. So the openings of those wooden lattices were changed to allow air from the bottom escape from the top, and also the building height would influence that. And if we go even a little bit further in history and look at the 16th century's Europe onwards, from providing houses that are built on rivers and where the air velocity is known to be the highest because it's unobstructed, and that would allow for natural ventilation. But if we even look at the size of the openings and the width of the plan, it's always for the richer, it's better ventilation, while the poorer would have the smaller windows. And this is even manifested whether you look at the Façades, you look at Chateau Chanson in the Loire Valley, and how really this is captured in the architecture expression. Going forward to the Parliament here, the UK Parliament, and how air actually also forms it's kind of a different expression because air is drawn to the bottom and then was heated and then circulated through the building and using this direct effect of buoyancy. But it's disconcerting because it really highlights that this quote mentioned by Adley, an analysis of air reveals who belongs and who does not, who is deserving and who is not in a constellation of megacity inequality. And if anything, this still unfortunately exists. So if we look at how air influenced the formation of plan sections and elevations of buildings, office buildings give us a good start to learn and look at how the U shape, the square shape with an enclosed courtyard, or the Chrysler building. You're still looking at 1930s multi-story building, quite complex, but naturally ventilated, to the movement of let's not share air. Air needs to be mechanized, controlled, and it needs to be mechanized to the point that we can import this architecture to anywhere in the world. And unfortunately, with all the good intentions of using technology, lifts, lights, the deeper plan to provide more financial gain from rentable area, but as you can see here, the New York Seaground building rated 3-star, which is one of the top bottom in 100 buildings in this category. But how air is used and expressed in buildings is quite interesting when we look at the 1950s idea of Buckminster Fuller, when he said that it's more ecological, more sustainable to cover the whole of Manhattan in a geodesic dome that would control the air inside. Not an idea that was discarded, but actually taken forward. So if you look at BDI's design in the Etihad Tower in Abu Dhabi, one of the hottest spots on Earth, how it's now being constructed and where air is totally controlled by filters and no natural ventilation is allowed at all. The elite do not share our air. But air is invisible and we need to quantify it. So we really need to use building and urban performance simulation. And we would have a lot of heated debates about this in between us, me and Peter. But we would look at how really the urban population is moving from 50 to 80% in 2050 to live in cities, with all the challenges that comes about with this kind of scenario, heat islands, and all the kind of different aspirations to use more complicated building forms and address ideas of the changing kind of occupancy, energy, pollution, and climate change. But we've also always looked at vernacular architecture as a successful precedent for for applying fresh air. But really, it's and interesting to know that through writings of people, of authors like Pilsama, we advocated that the sense of touch is very important. But actually, if you look at how branding works, the commercial branding works, there is this very influential statement from Lindstrom that says 80% of all commercial communications appeal only to the sense of our eyes. Yet 75% of our day-to-day emotions are influenced by what we smell. So if we look at vernacular paintings of Cairo, for instance, you would see that by trial and error, the commercial activities dictated an environment of fresh air, and this was manifested in how the roof was constructed. The more regular, the more higher quality timbers are used. That also reflected the type of merchandise that you have here and the quality of air. So keeping all the hot air on the top and the fresh air on the bottom of the market where silk would be sold in this case. But we also have to be quite careful with that, because we have to remember that climate change is affecting a lot of cities, and Cairo is one of them as a megacity, and most of the cities where the vernacular heritage exists are experiencing major changes, whether in their urban change or in the temperature where they originally existed. And if you look at the Max Planck's Institute, you would see that Cairo and Dhaka, where a lot of vernacular architecture and natural ventilation systems exist, are one of the most polluted cities. And then an opportunity presents itself to look at the differences between looking at renovated urban scale heritage and non-renovated parts, when the UNESCO attempted to renovate the eldest spine in Cairo, the Fatimid Cairo. That was the city itself is a small city among others in Cairo at the moment. And it was constructed in 1969 AD. And so the UNESCO renovated part of it, and as you can see, removed all shading systems, unified the facades, the shop openings, and really tried to gentrify it, while in the other non-renovated part, occupants and the users of the space were left to do whatever they want, and in this case, by trial and error, shading it with a retractable system. So we were interested to know which space would perform better. And through doing dynamic urban simulation, this is the spine, as you can see here, of the renovated area. This is the spine here of the non-renovated area. And you can quickly realize that the mean radiant temperature in the non-renovated part is performing actually quite better, with about maybe sometimes 10 degrees difference. So the unshaded part was really the worst scenario that was undertaken by the UNESCO. The trial and error in which responded to the historical paintings of the area was doing much better, but even better when we quantified it and studied this effect by using simulation and looking at another configuration that could be also used to cover the markets. Markets are interesting because they evolved, and in Cairo in specific, that the center of Cairo, most of you would have seen it in the recent presentation of the movement of the mummies to the museum. So it's a central part of Cairo was also designed by Haussmann, so it's known as Paris by the Nile. And in this area, there was a lot of image transportation of architecture. So the green indoor markets were introduced and as a symbol of providing a place for the elite to come and visit and do their vegetable shopping during the day. What was interesting here is that, again, trial and error provided excellent levels of ventilation. And as you can see here, the shops were able to maintain the outdoor temperature profile indoors without anything. This is different than talking about the thermal comfort in the cities here. But the natural ventilation was working, and most importantly, although outside the market at the moment, the levels of vehicular movement increased to very high levels, creating very high levels of carbon dioxide as a base, 586 ppm, rather than the usual 400, 350, 400 level. But the building itself, through its natural ventilation element and its expression of those natural ventilation elements, was able to keep the building as it is. But most interestingly, what we found out as a research team, and this took place with Cairo University, by the way, this was funded by the AHRC, that the revisitation behavior was actually influenced by the invisible environments that these buildings create. So the air, light and sound levels, but air played the most dominant feature in the appreciation of the building and revisiting it. While if you look at the shop owners who have been there for third generations, their story was a little bit different. They were more tolerant to what we would call suboptimal thermal comfort conditions and suboptimal air quality conditions because of the carbon dioxide that is transmitted in the air, but they looked at it with pride. And we found the same thing, that this issue of appreciating the building, that it gives us a sense of pride, has also had its implication when we were studying houses in Tibet, in China. So just to draw this to a closer zoom in on architecture, we now require a much higher level and much more challenging functions of the facades we design. So it's not just about being a climate separator, it's about being a climate moderator, and it's about providing healthy environments indoor, and of course, generate its own energy, be able to heal. And in this post-COVID environment, we wanted to provide higher levels of natural ventilation, but reduce energy demand. So this, I think, will be somewhat our next challenge. The idea of the building and its fabric having several layers is not new. And this is, Peter will be interested in this. This is one of the buildings in Harlem. And you can see here how the various configurations of the layers of the windows have different functions of ventilation and light. You can see how, now I will show you some of the examples of quite complex buildings. And I mean complex buildings because the more public buildings they are, the higher they go, then it's more complex it is challenged to provide natural ventilation. But in this case, they present different expressions. So in providing 100% fresh air to the MPs in the Portcullis House, designed by Hopkins in '99. That means that there is no air circulation, an intention to keep those MPs awake, the 213 MPs and their supporting staff awake. Then they also need to provide an expression of air where air is provided in the bottom, goes into a double skin and then into a chimney effect. Air cushioning in facades is well documented. It started by an idea of wanting to control sound levels, sound level transmissions between the outdoor environment and indoor environment, but then the cavity and the benefits that you could reap from controlling the air inside this cavity started to manifest themselves. So sometimes we use them for natural ventilation, sometimes we use them as an external duct to extract all the air outside the building. But as you all know, hot air always rises, and the whole idea now that it even has a further influence on our facade design, because we need to heighten the cavity more than the final floor, the top floor, to avoid overheating of that top floor. So double skin facades in this case started to play different expressions, and this is a project I was quite honored to work on. It's the Newcastle City Centre Police Station, and we use building performance simulation a lot to convince the team that we could provide natural ventilation without the challenge of introducing more sound, higher sound levels to the call center, which this was the new part of the building was going to be used for. And through building simulation, we managed to understand that air can be a lazy medium and it just likes to rise. So that lended itself that we did not put windows on top of each other, rather juxtaposed to allow for vitiated air to rise without short circuiting and affecting the health of other people inside on the top floor. You can find here that this is Sana and their La Samaritaine building. It's actually recently opened, and the idea that air also can carry fire fumes lend itself to having to declare where fire openings are found in this kind of facade. It also lend itself to a culture expression in the John Lewis department, and you can see here how the functional expression of the ornaments in this case, giving a nod to the cultural heritage of textile manufacturing by the Asian community. So another one, we can't talk about air without talking about Swiss Re, an iconic building, I have to say courtesy to Hilson Moran for providing their simulations and drawings. So a lot of an aerodynamic form that promotes views out and the original intention, and I have to say original intention, of providing natural ventilation through courtyards, and these are now called the office fingers, so 6 of them on every typical floor, but really trying to adopt this idea that we provide air as much as we can to the occupants. An idea that didn't end up well, because unfortunately one of those natural ventilation panels fell on the plaza in 2015, and of course the easiest solution was prevent natural ventilation, forget it, we have a mechanical system, that's it. And this wasn't, the idea of stopping natural ventilation was not really helped, because the office space had a mechanical system that circulated air. So in every finger, so fresh air would be taken from the floor, circulated in the cavity, and then pushed into, recirculated in the system through the plinth. As you can see here, the whole idea was providing mechanized air through each finger, so they can only use different parts of the building, very, very different from a traditional building where the air conditioning system is put on the top and circulates to the whole height of the building. So individual ones, but soon the occupants of the building started to complain of stale air. And this is an issue that is not uncommon in buildings that are controlled in this manner, unfortunately. And they from then stopped all forms of natural ventilation. And if we look deeper into it, the building services engineer provided the compliance with the regulation, in this case 5 meters per second, but instead of increasing the velocity, the idea was just stop it altogether. Another case where civic pride and significance plays a role in the architecture expression and how air is used. Another case of multiple layers of environmental veils in a building. And Manchester Court is a good example for this, where air is allowed in through this layer, a single layer, goes through the building and then finds its way on the west elevation to a double skin facade that also works with buoyancy. But in this case, what was quite interesting is the movement of air was decided based on what's public and what's restricted. So the public area here, because it is assumed that the visitors to the building would not spend a lot of time in it, they would go into the heating courts. So that would be used to extract the air from the building. But also to provide natural ventilation into the building, it was suggested that this is possible, and an air that is withdrawn from the environmental veil through the differences between the plinth of the false ceiling would then, in this case, provide natural ventilation and natural daylight to the indoor courtyards that are protected from the outside. Mild air, another way of expressing buildings. This is the Hafen City, Hamburg, Unilever building by Banish. And actually, this is an image that doesn't always represent the reality, because if there are ships, and there are various ships in here, the air pollution is quite significant. So it was decided to mine the air underneath the building, control that, filter that, and then provide it to the occupants, who are also compliant with the German rule of having no one away from an openable window by 8 meters. But unfortunately, similar scenario to what happened in Swiss Re, and natural ventilation, although works perfectly well, but still there are complaints of staleness of air. It also takes on quite an interesting twist here when Gensler worked with Bureau Happold on this PNC tower in Pennsylvania, where a double skin facade this time was actually used to provide natural ventilation even on the higher levels. So the air pressure doesn't become a problem here. In fact, it becomes a potential. And you can see that through a very intelligent and responsive BMS system, that the facade expression will keep on changing based on not just the level of air temperature and humidity outside, but also on the level of air pollution outside. So it completely controls the quality of air inside. And through those various studies, and this took about, I think, 4 to 5 years, so a substantial length of time, Gensler and Bureau Happold say that their studies show that through withdrawing air from those openings through the floor plate, they didn't want that vitiated air or used air to go into one atrium and then find its way to various floors. So actually it goes into closed ducts, and the buoyancy is encouraged by increasing the temperature of the top, so it sucks the air up even more. And it's claimed that it provides 42% of the occupied hours on fresh air. So we decided to look at this a little bit further and look at that kind of stratified air, and look with our research team, Ms. Yomna Al-Ghazi, myself, and Professor Martin D. Robinson, to look at whether we could use the stratified air to passively, so without any use of electricity, to operate a shading system with Nintol. So, and we looked at how the 3D configuration of these shading systems would help in this situation. Taking that into research, into teaching, I'm a firm believer that whatever we research has to have an implication on what we teach. And several opportunities presented themselves to work on live projects in and around Newcastle. So this was a live project with Sunderland Health Trust, and who were really noticing that their buildings were performing at a higher level of thermal discomfort, not comfort, because the buildings would rise to 24 degrees Celsius or even more. And as you can see here, this is a comparison between measured results, BMS results, and simulation with good agreement. So the students here were looking at various ways in which shading, natural ventilation could work to provide a more adaptive environment for those patients inside, and using principles of environmental psychology and looking at how this interaction works. We moved then to look at the frailty in architecture and how circulating air does have an effect on the architecture expression of that. So, and the students then realized that the output from building performance simulation can sometimes be quite difficult to communicate, and therefore started to visualize superimposing different layers of information on each other to facilitate this kind of communication of how they've used building performance and urban performance simulation to inform their design decisions. So here you can see, for example, that this is the form development, and then the air movement, and then how that leads to a pitch, and then how that pitch is optimized to deal with solar radiation, as you can see from here. So we're quite delighted that the RIBA started to take this agenda forward for making sure that all architecture schools in the country are integrating sustainability, a level of building performance simulation, and we're sure that this will help in supporting our already existing attempts to do that. A disconcerting note, I'm about to finish. A disconcerting note that air has a political ecology of its own. In urban areas, it needs to address the conditioning of air within interior spaces. The layered politics of urban atmosphere is not lost on real estate, and the real estate know very well that the higher you go, the cooler you get. So Stephen Graham just sent a very cautionary note about that. I would, on the other hand, like to send another cautionary note. As a concluding note to my talk, the most sustainable, energy efficient enclosure is the grave. It has a dead body, you don't need to keep it healthy, you don't need to keep it thermally comfortable. You can make the coffin from biodegradable material. It doesn't need air, it's dead. So that valuable material that we can only last without for about a minute is for us to design. Don't design the sustainable coffin, it's not your job. Let's think of not internet, not food, water, warmth, and rest as being the basic needs. We have to think that breathing is actually the basic need. And if anything, the recent COVID has highlighted that we need to evaluate our air supply mechanisms, how we express this in our architecture, and how we need to learn from post-occupancy evaluation without really the architects and the design team fearing litigation on the results of that. We all understand that. Hopefully, we're all trying to do our best, and we're not trying to float regulations. In fact, we're trying to provide better levels than regulations. An architect, if we look at its meaning in the dictionary, means a person who designs building, in many cases, supervises them, a builder, a planner, a draftsman. Can I please ask you to remember this? A breath of fresh air is a great thing to take, and an even better thing to be. So let's try to be the breath of fresh air. Thank you.
Okay, thank you, Neveen, for a very interesting and thought-provoking talk. And it is nice to kind of see over the years how your different projects come together and what a clear red line walks through it. I think I'll open the floor for discussion now. Louisa, I think we were going to invite people to join the panel. So if you can arrange that.
Yes. If there are people waving their hand, I will invite them to the panel. And at the same time, we are also, we encourage people to join our Q&A section. And also, you can also, our audiences can type their questions in the Q&A box, and we will discuss those questions in turns.
Okay, so let's start with whoever wants to join and ask questions live.